Well, we're going to start moving into a new part of fire protection systems. We have spent the first section of this class kind of getting a general overlook and talking about the first kind of fire protection systems. If you remember, I told you there's three different kinds. There's fire detection systems, fire alarms, which as of Sunday or this last module, we're done with that. Now we're going to move on and start talking about fire protection systems that extinguish, so fire extinguishment systems. And then lastly, towards the end of the semester, we will talk about smoke evacuation systems that draw smoke and heated gases out of the building. So in this second category, fire extinguishment systems, which we also call fire protection systems, we have three kinds: water-based, chemical-based, and gas-based. So we're starting a much bigger portion in talking about water-based systems. They're the most common, and they're usually the least expensive option. We only do the other kinds when there's a special need, but if we're going to use a water-based system, we got to get the water there. So thus here in Chapter 5, we're going to talk about the water supply for the water-based systems. How do we get the water to the building to use it to put out the fire? So that's kind of where we're at, and so let's get into it. So a lot of terminology that you're going to have to catch on to and things we're going to learn this week. So you really need to pay attention and pay attention to the new words. Words like fire load and fire flow. So the water demands of different communities are all very, very different. And engineers work through these things because every day, every week, every month, every year, the demands go up and down. And here in California, water's a big deal because we don't have a lot of it, especially in Southern Cal. So engineers need to determine when they're looking at fire protection systems, what is available. But even before that, other engineers are figuring out what the community needs in general and how we're going to get water from our rivers and our lakes and our wells to the homes and businesses throughout the community. So one of the things that they look at when they're considering fire protection systems is fire load and fire flow. So fire load is the stuff in a building that will burn. So these engineers will figure out, before even putting together a fire protection system, how much heat is going to be produced in this building as a result of a fire. And it's going to make a difference on how the building was built. Is it built out of concrete, wood? What's inside it? Is it just cans? I've been in a warehouse that was just full of empty Coca-Cola brand cans, little cans to be filled with Coke. But they were in this building just from one end of the warehouse to the other on pallets, empty cans. Not very flammable except for the pallets themselves. So it's going to have a different fire load than a place that might have plastics like a PVC pipe supplier or something like that, where there could be a lot of heat and a lot of gases that could be put off from a fire. So that's the fire load. Based on the fire load, they figure out, well, how many BTUs, how many British thermal units of heat is that going to put off? Then they can figure out, based on that, they know how much water it takes to absorb the different BTUs, because water has a fantastic ability to absorb heat. So how much water will it take to put out that fire? That's what they call fire flow. So fire load is the stuff that'll burn. Fire flow is the amount of water needed to put out that fire. So they're going to determine whether the water supply is adequate and whether we need more plumbing, bigger pipe, whatever it might need. So water supply systems, as we talk about them, first we got to start with how do we get the water to the community. So there are 3 different basic kinds of systems out there. Pumped systems are more common in areas that are close to a water source. Gravity systems are used a lot in communities like here in Southern California, where we have lots of hills around. But most of the time, you're going to find combined systems where they use both gravity and pumps together. So we're going to look at the pumped systems, we're going to look at the gravity systems, but basically a pump system supplies from a deep well or from a lake to the community. A gravity system is going to take a higher elevation and use gravity and the pressure that is increased by gravity and bring it to the community that way. So here's a diagram of a gravity-fed water distribution system. In this one, it's saying we're going to use the lake that is at a higher elevation. It's going to go down to a treatment plant, and then it's going to go down to the community, and we'll have used the increase in pressure from gravity, which is, okay, if there are any engineers in the room, don't hold me to this, but basically it's a ½ pound per foot. So if you have 10 feet of elevation where the water goes down, you're going to have a pressure of 5 psi from that 10 feet. If it's 100 feet off the ground, you have a pressure of 50 psi from gravity pulling the water down. Okay, that's just a round number that a lot of engineers use as a cheating way of figuring it out. So most of the time when we get gravity-fed systems, though, it's not from a lake down to a community that's at a lower elevation. We use tanks. And we take the water from different sources that comes either from a lake or from a river or from an aqueduct system like we have here in Southern Cal. And then we take it to tanks. And how do we get the water to the tank? Well, it comes from the plumbing of the aqueduct system and water supply that goes under the ground, and then it gets pumped into the tank. So sometimes these tanks are way up on top of a hill. We got to pump the water up to the tank. So that's why a lot of these systems are going to be combination, like I mentioned earlier. Now, what happens in this tank, if you can see that in the picture, that we have a tank and we have plumbing that goes up to the top, and there's a little stand up there for when they're going to service things. But inside the tank, there's a float. A little float valve, and the float is styrofoam or something like that that floats on the water, and it's attached to a valve. When the water is getting used and the tank is getting drained, the float will go down to a certain point where that triggers the valve and turns on the pump to supply more water into the tank because it needs more water to continue to supply to the people. So the water's going to go down from the tank, down into the community, into the plumbing that goes to homes and businesses. But it comes from the source into it via some kind of a pump that turns on when the float valve says, send more water. Here's a diagram of a direct pump water distribution system, and again, just standalone this way is not very common, but in a community that might be right next to a river, they can do this, in places along the Ohio, the Mississippi, and some of our other bigger rivers in the United States. They might have a pump house that's down at the river, pumps the water out of the river or lake up into a treatment plant where they treat the water so it's safe for us to drink and use. Then another pump pumps it up to the community. But usually what's going to happen is what we see in the next illustration. And that is we're going to use gravity and pumps together. So a combination gravity pumped water distribution system. Almost all of Southern California is like this. The water comes to us, excuse me, just had a little sneeze there, sorry. The water comes to us mostly from the aqueduct system from Northern California, where we steal it from the Owens Valley, and maybe water comes to some communities from the Colorado River. It also will usually come from a combination of wells and the aqueduct system. It goes to the treatment plants, and then we pump it to tanks. Now, in this illustration that you're looking at, it's a tank that's raised above the ground like we see in a lot of Midwest or flatland communities. Most of Southern California, we've got hills all over the places, so we put these tanks on top of hills. And it saves us having to put them in these big tanks above ground the way you see in the illustration. In fact, in our next picture, we see a typical gravity-fed system from a tank, but it has to have a pump to get the water up there. So as the demands of the community, as people are turning on their water and taking showers in the morning and things get going in the morning, and sprinkler systems are going, at irrigation that is, and businesses are turning on their water, the demand will start to, water will be going from this tank down into the pipes and to the different distribution and service laterals where it serves the community. As it goes down, the little float valve will get triggered and say, send more water. And so the pumps turn on and pump more water up to the tank. You don't want the pumps on all the time because once it gets filled, you don't want the water overflowing. So then when the float valve hits the top setting, then the pumps will turn off. And this goes on and off throughout the day. During the night, usually they get refilled and then they're kind of stable and they're not used as much. But during the day, it goes up and down and up and down and up and down, on and off, on and off. I had a friend who had a gravity-fed tank for his home and a pump down at the bottom of the hill. And all of a sudden, one day, they went to turn on the water and nothing happened. He checked the tank and the tank was empty. He couldn't figure out what the deal was, and then he went down to the bottom of the hill and found out that his pump had burned out and was no longer working. So he had to get somebody out to fix the pump, and then once the pump got fixed, it had to get turned back on to fill the tank. So he was without water for 2 to 3 days. They went and lived in a hotel while it got fixed. But this is typical of most communities, a pump to the tanks which gravity feed down to the community. And as this water comes down 100 feet or 150 feet, it gains and increases in pressure. And this way, we don't have to use pumps to get it into our homes. It just already has the pressure in the pipe system. So once we get the water to the tanks, now we need to get it throughout our community to all the businesses and homes. And so you can see here in this schematic from a community, there's a distribution network where we have transmission mains, and these are big 12-inch, 24-inch, sometimes even bigger, big pipe that distributes the water throughout the community. And then from the transmission mains, and if you think about it, where's all of this pipe? Where's all this plumbing? Well, it's not going, willy-nilly throughout the community. We keep it under our streets, because then we can access it if we need to fix anything. We don't have to tear down somebody's home to get to a pipe that's underneath their home that serves the community. They all go under our streets. So under the streets are all of this water pipes that go all over the place. So if you think about it, a big boulevard will usually have a big transmission main, something 18, 24 inches in diameter. Then as you go into your avenues and your smaller, but still pretty big roads that go into the different parts of town, then you get smaller. And these will be the distribution mains. And then as you go down your cul-de-sacs or down little streets, and it's going to serve and distribute off to different homes, that's where we get our service laterals. And these might be 8-inch or less in size. And another reason for going down in size, we don't need as big a pipe as we get down a cul-de-sac, but also by making the pipe smaller, we're increasing the pressure again. Just like when you put your thumb over the hose, and you can get more pressure for squirting on your car when you're washing it, it's the same thing. If you make the size that the water is going through smaller, then it increases in pressure and in speed. So for a distribution network to be effective, you've got to have it flow from multiple points to any point in the system. So what we're going to do is we're going to make it a loop system. And the plumbing is all connected with valves here and there. But that way, if one street has a break, we can shut down the valves, but the water still gets to most of the community by other ways, because it's a loop system. It's going through many different pipes to get to the whole community. Now, the water companies will always treat the water to make it potable. Potable means drinkable. Even though the water might be going to somewhere where it doesn't have to be drinkable, all the water in the community is going to be potable. So the treated water flows into these water mains, these big distribution or transmission mains, and so it goes from large to smaller into the distribution mains, and they go into those smaller areas. Then the service laterals take water from the distribution mains to the individual properties. And when it comes to your house, it might be as small as 1 inch. And then it goes into your house, and throughout the house, it might be 3/4 or even 1/2 inch as it goes to different faucets throughout your house. But if we're going to be supplying water for fire protection systems or fire hydrants or things like this, we want to keep that separate. So we're going to use the same water distribution system, but once it gets to the property, there's going to be one set of pipe that goes in to go into the faucets and the toilets and the showers and things of that nature, but a different system that's going to go to the fire protection. We don't want to mix those because the water that gets into the fire protection system sits there for years. And it gets gross, it gets black, it gets stinky, it's horrible. So you don't want that back into our water system. We're going to make it flow freely into anything that is being used for human use, but the fire protection systems, we're going to keep them separate. Now the water flows from different directions, like I said, in loops and grids, and this minimizes the interruption and it makes it easier to repair. So if you look at this diagram, this is typical of a community, and as I said, this plumbing will be under the streets, but notice how it's all looped and everything's connected. So if on one of these little streets they had a pipe break, and this has happened a couple of times on my street, well, we lose our plumbing for a little bit while they're fixing that. But not all the houses down the street, because they can isolate it by closing a valve on one side and closing a valve on the other side, and the rest of the loop system makes sure that everybody, other than that little section where they closed the valves, still has water. So it's called looped piping. Now, when we're going to do the fire lines and the fire mains, right at where the public water meets the curb or meets the property of the private property owner, that's where there's going to be a meter, right, that makes sure that you're paying for your water. But we're going to have two different lines, one for fire, one for domestic. Even in a business, they want to keep the water going to the toilets, the sinks, and maybe the water fountain. That's going to be clean domestic water. The water going to the fire sprinkler system is going to be separated, and I'll show you how they separate that. But there'll be two different mains coming into the building. We're concerned about the fire lines, and the fire mains, okay? So those fire mains are service laterals that then are going to feed water-based fire protection systems. So when, you might see the initials FL, that's fire line, or FM, fire main. A lot of times those initials will be used on the plans. All of this has to be done according to one of the NFPA standards. And we talked about the code's going to tell them they got to do it. The standard is going to tell them how to do it. So NFPA 24 tells the contractor and the fire protection system manufacturer exactly the details of how the water supply comes. Now there's going to be a different standard for the fire sprinklers, for the fire standpipes, but getting the water to those systems, that's NFPA 24. So the authority having jurisdiction, the approving authority, they're going to have their engineers who will work with the engineers for the company, and they're going to inspect, they're going to test, and fire inspectors might be involved in this, and they're going to certify any new public and private water lines, and then the fire inspector will work with them certifying or approving the fire protection system line, the fire main. So a lot of this is done through PVC pipe that will be just for the fire system. And in this picture, you see where they're backflowing gravel and they're going to put dirt over it, a fire line system that they put together. We're going to talk about how they use pipe. It's not, these systems, they're not going to use glue. They're not going to screw them together. They're going to use pressure to hold them together, and or they're going to constrain them or restrain them to keep them together. It's different than, because the amount of pressure and the amount of water flow, using any kind of a threaded system or a gluing system would not be adequate. You would have constant ruptures at the joints. So we'll talk about that in a minute. So actually a second, because here it is. So what they use is they use thrust blocks and or restraint fittings. And I'll show you a picture of restraint fittings. Thrust blocks are where they will use concrete underground anywhere where there's a change of direction in the plumbing. So basically the plumbing is all stuck together where you'll have a male end that fits into a female end bell housing, and they just kind of squeeze it in there. Now the problem is, if you didn't restrain it some way, as soon as you put water and pressure in there, they'd all just pop out and explode and all fall apart and water shooting everywhere. So what they do is wherever there's an end, wherever there's a 90 degree or a 45 degree or any kind of change in direction, wherever there's a T, like in this picture, they'll put a thrust block. And what it is a big concrete, like sideways pyramid, where it's in the ground with undisturbed earth around the back of it. And basically what it does is when they backfill, this is going to hold the plumbing together. The dirt on top of it holds it down, but this thrust block keeps it from moving when the water pressure hits that change of direction, the T, the 90 degree, or the terminus where it ends. And so they do these thrust blocks all over where they dig out the plumbing and place in the plumbing. So thrust blocks is one of the ways, and NFPA 24 tells them how and where to do it. It's so detailed because the soil in different parts of the United States is different. Some areas are really sandy, some areas are really rocky, some areas have a lot of clay. And so in these different areas, NFPA 24 even says how big and small the thrust blocks have to be and what kind of a concrete, how much concrete, how much sand, how much water has to be used to make it so that it won't move when they put water in it. The next way that they do it is they use these restraint fittings, and these are where they'll use nuts and bolts, and it's a pressure fitting. As they tighten it down, it holds the pipe together. Now, as you can imagine, using this ductile iron and all of those nuts and bolts, that's more expensive. So usually thrust blocks is used unless there's a reason to use restraint fittings, and a lot of times there's a benefit to using them even though they're more expensive. But as you can see in this 90 degree and also in this union between a PVC pipe and looks like some kind of a ductile iron or maybe even aluminum pipe, I'm not sure, but they chose to use restraint fittings. More expensive, but actually kind of more effective, but more often they're going to use thrust blocks. So that's how they kind of hold the plumbing together. And as you can see, in all of this underground plumbing these days, they're using heavy-duty PVC pipe. And the pipe has to be of a certain kind, a certain thickness, and all of that is laid out in the standards in NFPA 24. Okay, I got to pick up the pace here. So water distribution systems are going to have valves. And the valves are for turning on and off, not only just turn it on so that they have water, but if there's any kind of a break in the system, we're going to have to turn it off so we can repair it. So we need to have valves that control the water flow, not just on and off, but even maybe changing direction and things of that nature. So there are different kind of valves, and you have to be familiar with that. But basically, there's indicating valves and non-indicating valves. And the two kinds of valves that we see most common in these systems are gate valves and butterfly valves. So the valves control the water flow in the system, and they can control the direction of the water flow. A gate valve is usually one that is buried under the street or could be used in an OS&Y, and gate valves slide up and down with a screw that's attached to it and usually a wheel at the top. You turn the wheel, or maybe it's just a nut. And here, let me go back to that other picture. That T that you see there with the big long rod sticking into the ground, that is a key valve for a hydrant. So at the bottom, that is a fitting that goes over a nut. And then you can turn this key and turn on and off the hydrant. It takes like 20 to 30 turns, and it's very time consuming. And when a hydrant breaks off and the firefighters have to go in there and turn off the hydrant, they'll get drenched from this as the water's spraying all over the place, but it's basically the only way to do it. So either there's a street key or a valve key or a T-wrench that opens the valve, and these are usually non-indicating valves. An OS&Y is an indicating valve because the stem sticking out tells you, but it's also a gate type of valve. I'll show you a picture of a gate valve in a couple of secs. So if you look here at a fire hydrant, that's on a street, and see the thrust block at where the water goes up to the hydrant, and a thrust block that's where the valve is, and a thrust block where the water is turning from the street and going towards the hydrant. All of this is a typical assembly for just one fire hydrant. But what they're going to do is they're going to bury this valve, but they want you to have access to the valve, so they'll put that in a pipe type housing, but it can be, 6, 8 feet underground. So we need that big long T key valve. So when you see these little covers out in the street and it'll say water or valve, you pop that off, and there's a pipe that goes all the way down to the gate valve. Well, you can't get in there. You can't reach it with your hand. You have to use that key valve. You have to slip it in there and get it right over the right spot, and then you turn it. And like I said, a ton of turns, and then the water will stop flowing to the hydrant. So in our private water systems, we're going to use indicating valves wherever we can. A non-indicating valve is usually under the ground or something of that nature, where we can't see whether it's on or off or open or shut. So wherever we can, we want to use indicating valves, so firefighters or maintenance personnel can just look at the valve and see, is it open or is it shut? So a post indicator valve is a great example of that. A post indicator valve has a little window on it, and it'll either say open or shut. So when you turn the nut, it also turns this little sign that says open or shut. But a lot of times we see OS and Y valves. I'll show you a picture of an OS and Y in a second. But in an OS and Y, there's a big stem that sticks up. If it is open, the stem is up. That means the valve is up and the water can flow through the pipe. If the stem is down, that means it's closed, because the gate has slipped down into the pipe and obstructed the pipe from flowing. So that would be an OS and Y. They are all gate valves, and PIVs can be either butterfly type or gate, but these are all indicating valves. An indicating valve means you know if it's open or closed just by looking at the valve. So here is a gate valve, and it is also an OS and Y type of valve. So when someone turns that blue handle, the stem is going to come up and out of it, and by seeing that screw sticking out, that stem sticking out, then you know that the gate has been pulled up into that housing and the water is allowed to flow through. So that is a gate valve, but it is also an indicating valve, because you can tell whether it's open or shut. And here's another picture of a butterfly valve. One of them has a wheel type of handle. The other one just has a slide type of handle where you slide it a quarter turn or a half turn, depending on how the valve is made. And they can be indicating as well if there's something that, by looking at the valve, you know it says open or shut on it. So this isn't necessarily indicating unless there's something that shows you open or shut. So that big handle might have a place where it says open, and then you turn it and then it says shut. Also, if you know the direction of the pipe, then you also can know whether it's open or shut, because when the handle is going the same direction as the pipe, it's parallel to the pipe, it's obviously open. If it's perpendicular, it is obviously closed. but usually it's going to have the words open, shut, or open, closed. So these valves also can control the direction of the water flow. And there's check valves and backflow devices. So we don't want that dirty water going into our drinking water. So backflow devices keep that water from going back. It makes it so they have clapper valves that swing in the direction of water flow, and they'll only let water go in but never back out. So usually these backflow devices, nowadays they're going to do two of them right next to each other because they really want to be sure. Some of the older ones would be just one, and I'll show you a picture here in a second. There's two different kinds, double check valve assemblies and reduced pressure devices that when the pressure goes down, it shuts down. So here is a double backflow device, a double check valve backflow device. So those two red drum-looking things in the middle, they make sure water only goes in to the fire protection system and never out. This is all painted red because it's fire protection. Now the two valves that you can see with the chain hanging from one to the next, those are OS and Y valves. Again, they're gated valves because the gate goes up and down, not turns, but it goes up and down. So it's a gated valve, but it's also indicating, you can't really see it in the picture, but the stems or the screw is coming out of the yoke, and that shows us, just by looking at it, you see the big screw sticking out, you know it's open. If you can't see the screw, then it's closed. So it's an OS and Y. Now, in the front left side, you can also see a fire department connection. And that is where the fire department would connect to that. So you know that that side is the side that's going to the building, because they want to make sure that that also is not going to go back in the domestic system. So it's after the backflow device, making sure the water can't go back into domestic water, because it would basically poison it. It would basically pollute it. So the fire department connection is there so that we can increase the pressure in the standpipes or in the sprinklers. So when we have these systems, we're going to use them to provide for the standpipes and sprinklers and other types of devices, but we also need to have fire hydrants. So we're going to talk about fire hydrants here for a second. Most of you have taken the introductory course into fire protection and would learn about fire hydrants, but let's just review that. Fire hydrants is one of the most important parts of any water distribution network as applies to firefighting, and they're there to support the fire department in getting water on the fire. Local building and fire codes are going to require the spacing, the kind of hydrants, the number of connections on each hydrant, and that distance from hydrant to hydrant. Now, the local cities can get stricter. They can't get more lenient than the state. The state will have standards in the California Fire Code, but local counties and cities can make it a little stricter if they choose to, as we talked about before. Fire hydrants provide a way to connect for the fire engines and for firefighting operations. Upon arrival, the engineer or one of the firefighters will connect the hose to the outlets, run it through the fire engine where there's a pump to increase the pressure and supply the proper pressure to the firefighters. So once you open the hydrant, you remove the cap first. You apply the hose, thread the hose onto the hydrant, and then you're going to open it with a hydrant wrench. You never use a pipe wrench. It destroys the nuts. So I'm going to show you a hydrant wrench here in a second. So the water's going to flow from the hydrant through the hoses into the engine, and then the engineer will control the amount of pressure and the different hoses that it will go to for suppressing the fire. So again, I've showed you the hydrant T key. That's used for turning off or on a hydrant for repair. Usually we're not going to have to use something like that for firefighting. We use this 5-hole spanner wrench on the bottom right there, and it has 5 different holes for the different sizes of nuts on the different types of hydrants. There's also adjustable spanners, and I don't have a picture there of one of those. There's basically 2 types of fire hydrants, dry and wet. But there are some other versions out there. There's wall hydrants, flush hydrants, and yard hydrants. But most of the time, we're going to see dry barrel or wet barrel. The dry barrels are going to be for those areas that have colder temperatures where they can get freezing in the pipes. So they want to make sure that the water is below the frost line. A wet barrel, like we have here in most of Southern California, we're in an area where we don't get a lot of freezing, so the water is allowed to be right there, and each outlet can be opened independently. The water is right up to the outlets. Just opening the valve allows the water to flow. The downside of a dry barrel hydrant is once you open the valve, it's there in the whole hydrant. Any cap you take off, water's going to gush out. A couple other terms you need to know. Bollards are those posts that surround hydrants to protect them from cars backing into them and breaking off the hydrant. It still happens. Still people are dumb and aren't paying attention. I was in a restaurant and my wife says, "Holy smokes, what's that?" And we look out in the parking lot and a hydrant of water is shooting up in the air. And some person, I won't say what gender because it would be construed as being mean, got in their big stinking Lincoln, what are those called, Navigators, or yeah, Cadillac's is Escalade, yeah, Lincoln Navigator, and instead of putting her car in reverse, she put it in drive, and she drove straight into a hydrant that was in a planter, and boom, water shooting up in the air. She backed up off of the hydrant, but it was quite a display. It was like Old Faithful, a geyser shooting up in the air. So it still happens, but the bollards they'll put there to try and protect them from people hitting them, and it mostly helps. A wall hydrant is any kind of a hydrant that's installed on the structure. A flush hydrant is installed below ground in a vault and takes a special kind of device. I'll show you a picture. A yard hydrant is common in industrial areas, also where it would be below ground. So here's the 2 most common hydrants you're going to see are wharfs and steamers. A wharf hydrant is a single outlet, 2.5-inch hydrant. That one happens to be a dry barrel hydrant because notice that the nut is on top. If the nut is on top, it's dry barrel. So both of these pictures are dry barrel hydrants. The one on the right we would call a steamer hydrant. It's got multiple outlets, but it's also dry barrel. So once you open that nut on top, water is going to come into the whole hydrant, so you should have connected first. So this is a side note, as future firefighters, what should you always do before turning on a dry barrel hydrant? Well, the answer is kind of obvious, but you might not have thought of one part. First of all, you want to check and clean that you have good clean threads and attach any hose that you're going to attach. But I always say on the outlets that you're not going to use, instead of just leaving the cap on there, attach a gated Y, shut the gates, then open the main stem. Even though you're just thinking, I only need this 4-inch attached, but maybe later you're going to need more water, so why not attach a gated Y to that 2.5, and later on you don't have to shut down the dry barrel to attach another hose. You're already ready for it. So as an old engineer, that's a little 2-pointer from me. Attach a gated Y to the 2.5 and your 4-inch to the 4-inch and then turn it on. Make sure you shut those gates on the gated Y. Here's a picture of a wall hydrant. Obviously, it says on it, wall hydrant. Here's another type of wall hydrant with 6 different outlets, and those are all 2.5. Notice to the left of it is also the fire department connection for connecting to either the standpipe or the sprinklers. Now here's a yard hydrant, and notice that with a yard hydrant that's in a vault, you need a T-key to turn it on, and also you need a special device to connect into it and use it as a hydrant because it's all underground. Not very common. I've never seen one of these, but I know they're out there. I've just never seen one. Now here's another thing that if a construction company is going to use the hydrant or something that's not fire related, they have to go to the water company, get a permit, and get a meter. So they have to pay for that water. Fire department doesn't pay for the water when they're putting out a fire because it's good for the community, and the water companies provide that as a service. It's required. But if a construction company is using it to wet down the area or whatever, they're going to use a hydrant meter like that. So you might encounter this and see it sometime out there. The problem is now that outlet is no longer really available for us for use. We're going to use the 4-inch and the other 2.5. Different hydrants have different markings. Some communities, they will use different colors for different amount of pressure on the bonnet or top part of the hydrant. Sometimes in communities like LA County, they want you to put a red head on the bonnet of a yellow hydrant if it's really high pressure. But if your hydrant is a private hydrant, then the whole thing is painted red. That, I think, is a little confusing, but somebody else that wrote the code made that up, not me. So it kind of gives you an idea of what kind of pressure you're going to get, and private versus public is going to give you an idea just by looking at it by color. Sometimes we have locator flags in areas that get a lot of snow, and that is for the snow clearing equipment, so that they don't hit the hydrants. So those big markers will be there to show them where there's hydrants, make sure they don't knock into them. Okay, we're almost done. When fire hydrants are put in, they have to be inspected, tested, and maintained. So when a new hydrant goes in, we test it to make sure it's got the right pressure and that it is made correctly. But then every year we go out and we test them all. We open every single fire hydrant in our district, and we might even do a little maintenance that might repaint them, clean the threads. If anything is broken, we'll report it to the water company. If caps or plugs need to be replaced, we'll do that. If threads are really bad, we might report that to the water company and they'll replace the whole fire hydrant. As we've talked about, we need to know the pressure and the flow readings from the water source that will supply the system, and every system is going to be evaluated for adequacy. Do we have enough water? That flow pressure and the duration. Is it going to supply the water throughout a whole fire? So the water flow isn't just about the minimum, it's about the maximum. What's the maximum amount of pressure and duration that it would take to put out a fire? The system has to meet that. The pressure has to be adequate for the sprinkler that's all the way in the back of the building. So they do fire hydrant flow tests, and sometimes they'll reevaluate systems based on the needs. So, it depends on if there's any deficiencies. We might make them add a pump. I saw that with a church that had to expend the money to put a pump at the bottom of their hill. When they didn't have a sprinkler system, it was adequate. They put in a new building that required sprinklers, and they had to add a pump to their system, and it was really expensive, but the system wasn't efficient without the pump. We talked about the different kinds of water-based systems, and we need to understand that with that, we need adequate pressure. Now, we look at two kinds of pressure, basically, static pressure and then the dynamic pressure. So we want to know the flow rate and the gravity PSI increase and all of those kind of things. Well, what if the system is inadequate? What if we have a high-rise building and the water that's coming in is 100 PSI, which is great if we're at ground level or even a couple of floors up. But when we get up to the 80th floor, it's not going to make it. So that's when oftentimes they'll require pumps to be added to the building just for their fire system. So there's fire pumps, booster pumps. They're usually of a centrifugal type where they increase the pressure and add to it. Sometimes they might use a positive displacement pump, and we'll talk about the difference in them later on when we talk about pumps. But they've got to get adequate pressure to the different parts of the building, if it's a big building or a high building. Some of them will be jockey pumps. So a jockey pump is one that's just helping the pressure at a certain floor or just to boost it a little bit, whereas the big pumps at the bottom will be serving the predominance of the building. So these are going to require lots of drivers, controllers, switches to turn them on and off. They are very high maintenance, and that's why the facility managers have to be constantly checking them, periodically running them and testing them. The fire pump assembly components, there's going to be different relief valves, bypass, headers, test headers, flow meters, gauges, eccentric or concentric reducers, increasers, because all of this depends on where they are in the building. When you're going up 80 floors, that's 800 feet, right? 10 feet per floor. That's 400 PSI needed just to get it to the 80th floor. So we're going to have all of these different kind of things to take care of that. The fire pumps need to be operated periodically and will turn on whenever there's a sufficient loss of water. They've constantly got to be inspected, tested, maintained, and serviced. Okay, so we learned about different parts of the country are going to have different needs for water supply systems. We're going to use different kinds of distribution systems where we use pumps and tanks and gravity fed. We're going to have to treat and purify the water and then send it through some kind of a distribution system. The water supply system supplies the water for the community's domestic, commercial, but also fire protection needs. So we're going to supply to fire hydrants and to fire protection systems. When we have a dedicated fire line or a fire main, we're going to separate it. The only exception to that is residential fire sprinklers. We'll talk about that later on. So the water supply goes to the hydrants and to the fire protection systems, and there's a big demand there. We got to make sure that they get it all there, so we're going to use valves for repair and controlling the water mains and the water lines. Fire hydrants offer firefighters a ready water source for firefighting. We got to make sure that they're the right kind, properly spaced. And the two most prominent types of hydrants are dry and wet, and we talked about that. Water flow tests have to be done on all systems, not just hydrants, but sprinkler systems. We're going to test the pipe. We're going to test the different valves and make sure that everything is working the way it's supposed to work before we approve it and allow the building to be occupied. Lastly, to overcome any pressure problems, we're going to add gravity tanks or pumps to systems to boost where we need it, especially in high-rise buildings or very large buildings like a Walmart or a Costco, where they're extremely large and we need to have water all the way to the back of the building as well as to the front. Okay, sorry that was a little longer than I hoped it would be, but this is a really important one, understanding how the water gets there. Don't forget to work on your pop quiz, and hey, I'll see you next week. Contact me with any questions. See ya. Bye.